Here's an example of an Atwood machine. In other words, every time we have two boxes attached to a string that goes over a pulley, we talk about an Atwood machine. In this particular example, we will have two objects connected with an inelastic rope that is hung over a massless pulley. If the mass of the object A is 2.0 kilograms and the mass of the object B is 3.0 kilograms, the question will be to determine the acceleration of the objects as they're going up or down and the tension in the rope. So let's see the diagram, how they look. Here's the pulley, the massless pulley, and the rope across it. On the left end, I'll just mark the object A, and on the right will be my object B, because the problem gives the mass for the object B to be 3 kilograms heavier than the mass for A. I expect that B will be moving downwards while A will be going in an upward direction. First, let's start with a couple of facts. The first thing is that as B is falling down and A is going up, both objects have the same magnitude for their acceleration. Yes, the vector is different. In fact, it's in the opposite direction, but in terms of magnitude, they're moving with the same acceleration. And that is because the rope is inelastic. The rope does not stretch, so it kind of couples their motion. If A goes up 1 meter, B has to go down 1 meter, otherwise the rope will stretch. And that motion, that displacement has to happen over the same amount of time, otherwise the rope might break again or stretch, and that of course couples their velocities, and of course it couples their acceleration. So let's mark the acceleration. A being the lighter object will be having an acceleration upwards, and B being the heavier object will have an acceleration downwards. So here's the vector for B. The second fact is that the tension in the rope on both sides of the pulley is going to be the same. In other words, that stretching of the rope is the same regardless of whether it's on the left or right side of the pulley. That actually comes directly from our assumption that the pulley is massless. Later on, if you ever solve problems from rotation and the pulleys, and you have to consider the mass of the pulley, the situation becomes a little bit more complicated. But for now, we're going to consider that the pulley is either massless or it's so light that we can actually neglect its mass. So because of that, I'm going to mark the tension in the rope, especially where that rope is attached to the two objects, so object A and object B. I will draw two vectors pointing upwards. They will belong to two separate force diagrams or free body diagrams when I'm analyzing the motion of each object separately. And so we're ready to actually focus on object A, let's say. I'm going to add here the vector for the gravitational force that acts on A downwards. This is the vector G. And then I'm going to select a coordinate system, standard, very natural choice, x to the right and y up. But looking at all my vectors, including the vector for the acceleration, they all align in the vertical direction. So actually, I don't really need that second axis. And the problem becomes a one-dimensional problem because everything happens in the vertical direction. That will be my only axis here. So let's go around and see what those components are, the vertical components of the vectors. The gravitational component will be minus the mass of A times G. The vertical component for the tension, I will mark it as plus Ft. That tension is pointing upward, so it's going to have positive component. And the acceleration vector also points upward, so it will have a positive component. So I'll mark it as plus A. So with that, let's I can actually apply Newton's second law for the object A. Remember, we will have only one equation here for the y components, and that will look like this. Minus mag, that will be the gravitational vertical component, plus ft, that's the tension, has to be equal to plus ma times the acceleration. So here's my first equation. I have two unknowns here, the tension and the acceleration, so I need the second equation. So I need to go back, I need to go to the second object here, B, and draw our coordinate system x, y for my forces. But once I draw the vector for the gravitational force downwards, I see again I have three vectors, two for the forces and one for the acceleration, and they're all aligned along the vertical direction. So once again, I can wipe out my x-axis and work only with the y components, which will be minus mbg for the gravitational vector, plus ft for the tension vector, and minus a for the vector for the acceleration. Notice that here, because my positive choice here is upward, but the acceleration of the heavier object is downwards, its y component is actually negative. So, and that is how I have to treat it in my equations when I go to Newton's second law for the object B and add all the y components. They have to add up to the product of the mass of the object times the acceleration. Specifically, I will have minus mb times g plus ft will be equal to minus mb times a. Remember, minus a here is the y component of the acceleration of the heavier object that is falling downward. So there's my second equation. And so from here on, the rest, what I have to do is simply algebra. I'm going to combine the two equations into a set of equations that I have to solve simultaneously. From here on, it's really up to every individual student how they want to go about and to solve that set of equation. The question here, from now on, the steps are purely mathematical. The physics is over in a sense. The two unknowns here are the tension and the acceleration of the objects. So we have two equations, two unknowns. My personal preference when I solve this type of set of equations is to go through the method of elimination. And so to that end, I'm going to take the left-hand side of the first equation and subtract from it the left-hand side of the second equation. And that has to be equal to the right-hand side of the first equation minus the right-hand side of the second equation. Let me show you what happens. I'm going to open the parentheses here. So I'm going to have minus mag plus ft. Minus minus will flip to plus mbg. And here I'll have minus ft. And that has to be equal to simply the sum of the two masses. I factored out a here. Even more so, the tension cancels out, and that was my reason to go for the elimination method. Sometimes students prefer to go simply through substitution, express one unknown through the other, and plug into the second equation. There's no better or worse method. Whatever is the best for you, or whichever method you're most comfortable with, go ahead with that. I'll go here with my way of doing the algebra just to show you what we get. So on the left hand side, I'm going to have mb minus ma times g. I factored out g here. And on the right hand side, I continue to have the sum of the two masses times a. So that gives me, for the acceleration in symbolic way, for the object in the Atwood machine, to be equal to the difference between the heavier and the lighter masses. So this will be mb minus ma divided by the total mass of the system, ma plus mb, multiplied by g. Numerically here, if you put 3 kilograms, substitute 3 kilograms for mb and 2 kilograms for ma, you will find out that the acceleration here will be 0.2 g. I kept g here. You can plug in 9.8 meters per second squared for g and find the numeric answer, but I kept it here. It was easier for me to do it without a calculator. So what about the tension? So what I need to do is I need to grab this expression for the acceleration. I need some more space here, and use it in one of the original equations. I chose to use the first equation, the top equation. So with that, let's see what the top equation looks. It's going to be still minus ma times g plus ft, and it has to be equal to ma times the acceleration. Only now I know the acceleration is going to be the difference between the two masses, mb minus ma, divided by the sum, ma plus mb, times g. Normally, if I were doing this problem by myself and I had the numeric values of the masses, I'll just plug the numbers and get the tension. But I want to show you the pattern. What is the expression for the tension in the Atwood machine's problem? It's not some arbitrary numeric values. There is some deeper pattern there, what the tension is. So let's do a little bit more algebra. I'll move the minus mag from the left-hand side to the right-hand side of the equation, and that will give me that the tension the force of the tension has to be equal to MAG plus whatever was the remaining. In that fraction, I actually distributed MA, so I have MA times MB minus MA times MA. In the numerator, the denominator remains equal to the sum of the two masses, MA plus MB. The next step is to actually bring the two terms on the right-hand side of the equation under the common denominator. And in that case, for the numerator, I'm going to get MA times MA, which will be MA squared, plus MA times MB. Then I have to add what I already had in the numerator before, plus MA times MB minus MA squared. In the denominator, I will have MA plus MB, and don't forget that I have this factor of G that multiplies the entire fraction. The reason I wanted to do that is because I wanted to show you that things are not as complicated as they appeared at first glance. MA squared will cancel out, and then we simply have two terms that are actually identical, so I can actually write that in my numerator I'm going to have 2 times the mass of A, the mass of B, divided. So in the denominator I'll have the mass of A plus the mass of B, and everything will be multiplied by G. That will be the value of the force for the tension. So you can see this problem with many different number of values for the masses, but ultimately you can use this as a quick reference or a quick checkpoint and to get to the answer. Unless you're solving a problem in which you have to show you steps, you can actually use that. So numerically, this will be 2 times the mass of A, 2 kilograms, the mass of B, which is 3 kilograms, divided by the total mass of the system, which is 5 kilograms. And so, and G, of course, is 9.8 meters per second squared. So that gives us for the tension 23.52 newtons. So now I'm ready to write my answers here, final answers with the standard standard 3-digit notation. So for the acceleration, for the magnitude of the acceleration of the objects, remember, one of them will be going upward while the other one will be downward, but they both will be moving with the magnitude of their acceleration equal to 1.96 meters per second squared. That was really the 0.2 g, and the tension in the rope will be 23.5 newtons.